Hello to viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about deeper dive into BMS, yani ki Battery Management System. So let's dive deep into it. So why the heck do we need battery management system? Well, reality is the world is getting addicted to battery power. Our vehicles are getting battery power, our drills are getting battery power, our grids are getting battery power. So yeah, so what the heck is a battery? Like, for example, is this a battery? We may call it battery, but it's not a battery, it's a cell. If you add two of these puppy, now we are talking. So for example, is this a battery or a cell? Is it a battery? Yes, absolutely, it's a battery. Why? It's 12 volt. Lead acid does not have that kind of voltage. It has 6 cells in it. So this is what we call a battery. Battery is just a pack of cells. Now you have to understand this. Even in lead acid, no two cells are alike, meaning if it has 6 cells does not mean all 6 are behaving exactly the same. I have 2 lithium ion battery made from the same batch, same chemistry, same company, same everything. Does that mean they will be same? They will be close, but they will never, ever be perfectly same. Like if you have a low grade manufacturer, the cells could be literally one cell to another cell could be off by 10%. If you have good branded cell, like but like low cost, it could be like 5% off. Very high quality one, you are looking at like 1 to 2% off, but it always be off. Sometimes you may luck out, you get a bit more capacity, sometimes you will not. It's a law of physics. Do not fight it. It's there, it's real. That's it. That's what it is. Now when we used to deal with lead acid battery, we used to build huge system like lead acid battery system. Like this is 12 volt. Heck, we started with 6 volt, we went to 12 volts. 24 volts are common in like household electronics. I have 24 volt inverter. Many trucks and big puppies have 24 volt electronics. So, and solar inverters, they also go in very high voltage, but we never worried about balancing it. Why? Well, you have to understand, this puppy, it does have a boom potential, but that happens because of water leaking this puppy and then it going kaboom. But generally, these are very tolerant to over voltage situation, meaning if you give them, let's say 13.5 volt, they're like, yeah. If the cell reaches a point where it's like, oh, I'm fully charged, you do not actually need to disconnect it. The energy will just like keep filling up. Like it will reach a point where it's a equilibrium. It's just wasting all the energy as a heat, but it will reach equilibrium. So it's safe. Same happened with nickel metal hydride batteries. However, lithium chemistry, it has far more energy, but this puppy is freaking sensitive, man. Like if you abuse it even a little bit, at best case scenario, you're gonna wreck the battery, meaning it's not gonna work anymore. At worst case scenario, yeah, this happens. And yes, this happened in NASA. And yes, that's a Tesla in China. Yes, that's a Tesla in America. So you get the point. Basically, these puppy do not tolerate abuse. You undervolt them, you overdraw power out of them. Overdrawing could lead to those things. Undervolt would mean battery bye-bye. It won't work anymore. So you have to understand, these puppies are sensitive and abusing it is not an option. Now you have to understand this another aspect. It applies to everything. Anything that stores energy fundamentally has the ability to release that energy. Otherwise, you would not use it. So, for example, if this cell is fully charged, this cell is fully discharged, safe level, everything is safe. You penetrate this puppy, it will go kaboom. If you penetrate this puppy, same chemistry, same manufacturer, same everything, this will just go. So you have to understand, it's like the only way to make it safe, you have to reduce the energy that is available. That's why lithium ion and lithium polymers are classified as naughty puppies, while lithium iron and lithium titanate oxides are considered as safer puppies. Why? They fundamentally have less energy. So oops is far more less oopsie. Like for example, the electrolytes here, they are at much higher potential. It could be like 4 volts, meaning things could electrolyze, things could separate. And given the fact that it has both sides, so basically the things that burn, the things that oxidize, both sides, it's a bad thing. So fundamentally, you have to understand lithium. And if anybody says like, what if we are gonna have solid electrolyte or this or that? If it has high energy, run. Like run. To give you a mathematical context of it, the sole reason we can use fuel, it's half of it. Fuel is half, other half is oxygen. We do not have liquid oxygen. If you have liquid oxygen, you have a rocket engine. What do you think has more power, RDX or petrol? Petrol. But petrol is contained because of the nitrogen in the atmosphere, so it's safe to use. RDX, good luck. So that's why. That's a fundamental law of physics. You cannot bypass it. No two cells could be alike. And if the cell has power, it fundamentally has the ability to dump that power. So that's why when they were saying like if you have a defective cell, discharge it. That's the reason for it. So that's the why we need balancing. Let's come to the battery part of it. Now, how can you make a battery? Well, you have simple options where you can connect the cells in series or parallel. Like series like this, remember old torches used to do like this, or parallel, basically you have something like this, basically positive to positive, negative to negative. So series to parallel, I'm pretty sure if you have crossed class 10, you must have already know this. Now if you are dealing with something very high power, there's a good chance you may have both of it, meaning you have some series, some parallel. And that's why anybody who's building battery banks, they say very weird things where it's like, 4 series, 6 parallel. It's like, what the hell? So to simplify it, when you add in series, you increase the voltage. When you add in parallel, you increase the capacity. Now you may be like, wouldn't it be wise to use a bigger cell for more capacity? Absolutely. And you can see that, like, for example, early Tesla used to use 18650. Then they upgraded to 21 series. Now they have upgraded to 70 series. So it's always the same thing. You will try to use as big of a cell as possible. But what if you can't find the cell? Or cost. That's a very important thing. If cost is too high, then what the hell you gonna do? Sorry about that. So in those sort of scenario, the only choice you have is, like, let's say you added 2 of it. Now you are happy with the voltage, but you're not happy with the capacity. What if you added 1 extra in the parallel? Okay, now you have double the capacity. So that's how we do. In high power application, generally you get things like this, which could literally be, this could be one cell chemical, voltage wise speaking, another could be another cell, another could be, and all the cells could be in parallel. So we use that in very high voltage and system. Now parallel is great. That's why we do it. It's super easy to do. You just basically positive to positive, negative to negative. It's super easy to do. Because it's self-charging, basically self-balancing, meaning, for example, let's say what happens when a battery is discharged. The voltage drops, right? You will start at 4.2 volt, it will drop to, let's say, 3.5 volt. But here's the deal, the cell capacity is not balanced, meaning you drain the same amount of watts, but one dropped higher in voltage, other did not, because again, one capacity was lower. So you could literally have a scenario where one cell is at 4 volt, other cell could be 3.5 volt. What do you have? You have an imbalance, meaning potential difference. What is potential difference? Is voltage imbalance, basically, right? That's why we call potential. What is the gap between A and B, or high point and low point? So if you do that, like basically one is like at 4 volt, another is 3.5 volt, that means you have 0.5 volts. What does nature does not like? It does not like that unbalance. It always wants to equalize it. So energy will flow from both of them to balance it out. Whichever direction it needs to go to balance it out. So this will happen. So it auto balances it. Most power banks in the early days from 2010 to 2015, and not even 15, I would say till 2020, they were using a lot of parallel cells. It was much more efficient and safer to just use a DC boost converter to go from, let's say, 3.5 volts of using the battery under load and boosting that to like 5 volt, 15 volt for needed for fast charging. Because again, the more cells you add, the more capacity you get, but you do not have to worry about balancing it. Parallel self-balances. But if you add it in series, which nowadays people need to do, because again, 48 volt we need for USB-C power delivery extended range, that puppy requires a bit more oomph. Boosting that much, can you boost it? Absolutely, it's just too much. So at that point, people are like, okay, the cost of BMS is now economical. So parallel is self-balancing. That's why we can make parallel as much as we want. So whenever you're talking about battery pack, that's why you only focus on the series part. The parallel part, yeah, of course, some circuit will say, hey, if you are connecting it to something that has too much too high amp power, it may behave erratically, but most of the time you will be good if you pay attention to the series part. 4S, 5S, 6S, that is the series part. How do you calculate? Well, nothing serious. Like if somebody says 4S, S is the value of your cell, multiply with that number. So 4S means 4 multiplied by 3.5 volt if you want to calculate the nominal voltage output. If somebody says 4P, you don't have to worry about it. It's just like, oh, one, let's say this puppy is 2 amp power. That means if it's like 4 amp power. So basically P is the capacity, S is the voltage. You just multiply with the number. So that's how you get the what exactly is the capacity. So parallel is great. However, when you need higher potential difference, higher voltage to get more work done, like how these puppies needed 6 of those puppies to make 12 volts. In those sort of scenario, you need balancing. Now, issue with balancing is that you need to study every single cell. Meaning, what is this cell voltage, what is that cell voltage? Because energy does not self-equilibrate. You need to know, okay, one cell has dropped to 5 volt, another has dropped to 3 volt. You may detect outside the total voltage will obviously drop, but you do not know is it dropped balanced or unbalanced. If everything went down, awesome, do not worry about it. That's how lead acid works. But when you are talking about lithium, you could literally have a single cell going lol and causing the whole battery to cut off while it has energy left. So it would be like you filled the water tank with 100 liters of water. You only managed to drain 50 liters before it cut off. Why? Unbalance. So parallel is great, but we need to balance it. At series, we need to balance it. So you need leads. That's why you will always say lithium ion polymer. They will have two positive and negative, which is the power rail, and they will always have leads. That lead supposed to be connected to balance charger. That's the reason for it. You need to study the voltage of each cell. Now, on top of that, each cell chemistry is also unique. For example, while we say lead acid and lithium ion has a very different curve, that is true. But inside lithium ion itself, you have multiple chemistries. So this is a very simple graph that people used to show. That is lithium iron oxide, lithium iron phosphate. Lithium iron phosphate, you have nickel, cobalt, aluminum. Then you have lithium titanate oxide, nickel, manganese, cobalt, and you can see like you have specific energy, meaning how much capacity it has, specific power, how much oomph it can have. Like capacity would be like how many liters of fuel you can have in your tank, versus specific power is like how much horsepower your generator can produce in short burst. Then you have safety. What is the likelihood of oops? And how does safety is measured? Well, safety has like one absolute failure point. You puncture this, it's bye-bye. Another thing is, what is the likelihood of electrical failure? That can be quantified. So what you want is anode and cathode that are stable at very high temperatures. Generally, basic cells are capable of surviving 150 degrees Celsius. So if you detect 100 degrees Celsius, run. So if you have better chemistry, it could be able to tolerate, let's say, 175 degrees, even better, 200 degrees Celsius. So the run away is pushed away. That's all we are doing. So that's the safety vector. Then you have performance. How many cycles it can do without degrading in terms of capacity. Then lifespan. How many cycles before it loses 20% of its capacity, drops to 80% of its total power. Cost. So for example, lithium titanate oxide gives you the most specific power, safety, performance, lifespan. That puppy lasts for 10,000 cycles, so it's bonkers. Lithium iron oxide is somewhere between lithium titanate and lithium ion. It is also gives you very long lifespan, has a lot of performance, has very high safety, has very good specific power, but in specific energy is very low. This puppy does not. Basically, if your battery box has to be huge, very heavy, in order to have the same amount of kilowatt hour to compare against a basically nickel cobalt system. That's why cars started with lithium iron, because again, people were worried about it, but people are like, hey, we want more range, more range, more range. So they're like, okay, lithium ion. Now people are like, okay, let's go back, because again, it started to catch on fire. So fundamentally, all these chemistry have their own curve, and battery management system has to deal with it. The worst thing to balance is lithium iron, because it has almost flat curve. Basically, if your flat curve happens, you may have one cell that is literally has 5 amp power capacity left, another could be 500 amp, the voltage would be same. They could literally have that flat of a response. So it's really, really hard to balance. So you generally prefer to bottom balances or top balance it. And be mindful, almost all cells do that. But some curves are like bit more granular in voltage. So if you study the voltage correctly, you can estimate what kind of state of charge is there. Lithium iron phosphate is the worst in that regard. So that's the battery side of things. And each of the curves have to be studied, analyzed. Only then you can make a BMS that is absolutely perfect for it. If not, sloppy output. Then we come to the first thing that people do most of the time when they are trying to build it, study it or whatever, is something like this, passive system. Now passive is a low cost. That's why people do it, because it's a very low cost top balancing system. What does top balancing mean? Be mindful, all lithium ions have a very flat curve relative to lead acid. So it simply means you do not have enough voltage to make sense of it. So what you do is basically wait for all cell to reach a top voltage, as in around 4.2 volt, and then you trigger a resistor. The moment a single cell reaches a point where it's like, bro, I'm fully charged, you could still have like 1 or 2 cells that are not fully charged. But if you let it happen, what will happen is the pack voltage will reach a point, and battery management system would be like, battery is fully charged. It's like, bro, one is not fully charged. So that could happen, or worst could happen is like it detects over voltage on cells and it's like, okay, let's cut it off. In both scenario, you did not charge fully. And if you have a one weak cell will single-handedly trip your system. So the useful energy would go down. So this sort of board you apply, the useful energy will go down drastically. You will be like, hey, first time I charged the battery, I got to run it for, let's say, 1 hour. That's time, like few days later, then it's like I'm barely running it for half hour. Few days later, it's like barely 15 minutes, it cuts off, because again, one weak cell can drag the whole system down. All it does is like a cut-off system. So what we do when we charge this puppy, you have a resistor connected to it. So once the cell voltage just reaches the full charge system, And generally lithium ion has what we call constant current, constant voltage. Once you cross the constant current part, the voltage is high but the current is very low. So at that point in time, a small amount of resistor is used as a bleed energy, meaning a microcontroller would be there, it's connected to the cell, it's studying the cell, it's like, hey, the cell crossed 4.2 volt, it's reaching over volt. It will be like, okay, let's use a MOSFET, dump all the excess charging energy into the resistor gets hot, the cell is calm, cell is like, I'm good. So it just bleeds off energy. So if you are dealing with big pack, you have to use a bigger resistor. So this is a DIY system. The resistors that they are using is upwards of 10 watt. You have to dissipate the charging energy. Thankfully, charging energy is much lower in the constant voltage regime, so it can be done, but it is flat out wasteful. You are balancing it, and it only works generally during charging time. Can you do this in discharging time? Not likely, because again, you are drawing the energy away. So dumping that energy to balance it is like, you're just wasting capacity of the fully charged one. It's like generally it's done during charging, and that's why you will always have leads of battery plus, battery voltage number 2, voltage number 3, voltage number 4, then you'll have the full pack. So in this scenario you can easily see 4.2 volt first cell, you can have 8.4 volt the second cell, 12.6 volt third cell, and then you can have the positive negative output out of it. So it just basically dumps the energy through resistor. It's very wasteful, and it needs to read all cell voltage. So if you directly connected the most positive, basically 0 volt and 12 volt, will it work? Yeah, it will be unsafe if you do that, and most smart BMS will not allow you to start running the system. It will like, bro, I need to study the voltage. So it does work. Now it's a very good cutoff circuit, meaning if something draws too much amp, like whenever you buy board like this, generally they also have that extra amp fuse. So for example, this puppy would like 40 amps. You draw more than 40 amps, it's like, nope, it cuts it. So it's very good. It detects one cell going too low in voltage, it nopes it. If you have a cell going high voltage, it nopes it. When you are charging it, it detects one cell overvolting, it dumps the energy through resistor. Now it's a very good cutoff system, very low cost, but it should only be used for very low power. Meaning if you are using something like this or for high power, no, just unwise. That's flat out unwise, especially if you are building your own pack. If you are buying something like, let's say, very top quality battery made from the same factory, every cell is very close to each other, then yeah, this sort of system would be good enough. But in long term, especially for the people who are building it themselves, or again, you want your system to last long, this is not a good system. So this is like a starting circuit. It's like, oh, you started, then you move on to something else. So this is a starting point, not a wise use, because again, fundamentally you are wasting energy and you are not balancing during discharge. So literally people will have this like, hey, I built this, it was super awesome for one or 2 months, and then it's like, hey, I'm getting half of that, and then yeah, it's dead. Because it's not balancing it. Balancing it during charging is also not that wise way of doing it, because you are literally wasting everything away. And most of the time the resistors cannot generally dissipate enough energy if you put them in large banks. So consequence would be it will trigger cutoff before it triggers basically balances the cell out. That's why again, all it has is a resistor to waste energy. Unwise. So we come to the active system. Now active system is what we call cell equalization. Basically it detects, hey, one cell is higher voltage, another cell is lower voltage. It's not like let's waste away of energy of the high voltage. Let's take that energy, dump it into lower one. So that allows the unhealthy cell to be discharged, dump the energy into healthy cell, which will absorb the capacity and be like, hey, everybody is good. So that's what we call cell equalization. That's the end game, and it's far more efficient. So if you are trying to take charge away, dumping it on another cell, of course you will waste some of it, but that waste would be some percentage rather than what are you doing? Okay, I'm connecting a resistor as a heat load. So fundamentally far more efficient. So if you have a very sloppily built system, you are looking at 70% efficiency. Some well-built, well-tuned system, 90% efficiency when it's equalizing. So very efficient, useful. Now it works both in charging and discharging. So fundamentally it allows you the most amount of life out of your battery pack. So your battery pack, like, oh, I had 100 liters of capacity, I get 90 out regularly for years to come. Years to come, you will be like, yeah, I'm getting it. And when it drops, it will not drop just wabam. It will drop very slowly. You will actually be able to use it for much longer. Even though you spend more money on this, it will pay itself off, because that's how long you get. And especially for people who are using unbalanced cell. So, and it works both in charging and discharging. So it's a really, really wise system of doing that. And it works based on voltage differential. So both system, basically you have two types of system. Both of them require voltage differential, meaning lithium ion and lithium polymer, they are the perfect to balance in active circuit, because again, the voltage drop is very almost like a capacitor. relatively speaking. I know it's not an absolute line, but from a balancer's point of view, it's like enough voltage difference is there between a charged cell and partially charged cell. There is like, energy can go from here to there. Lithium ion is very hated for this reason. For that, you may need an extra circuit that just turns it on when it detects that, okay, now single cell has reached an unstable point, or either it detects imbalance between majority of the cell are healthy but one cell is unhealthy, the balance is off. It's like, okay, started the system, or it's like everything is fine, but it's waiting for the cells to reach into the discharge value, the bottom discharge, then it balances it, or reaches the full charge, then it balances it. Basically, it will not work in that mid part. Now, there are two primary tools for doing it. First tool is capacitive active balancer, this sort of puppy, basically giant capacitors. So what it does is scary. How the heck any human figured it out that this can be done is that there is an oscillator behind it. So what you do, you have all the voltage leads. These leads are connected to the basically cells. Each cell is connected through a switch, as in like MOSFET. So cell goes there. The capacitor gets the voltage of the cell. So cell is 4 volt, the capacitor gets 4 volt. Cell is 3 volt, capacitor gets 3 volt. So everything is connected to the cell. Okay, you disconnect it. So you charged up all the capacitor to the battery voltage, cell voltage itself, and now you disconnect it from the battery. Now you short all of them in parallel. So basically you connect the positive rail and negative rail of all the capacitors simultaneously. Now what will happen in that? Well, again, nature does not like unbalance. It will reach equilibrium, meaning basically the capacitor that was connected to 3 volt will literally go up in voltage, and others that were in high voltage, basically they were reaching 4.2 volts, they will drop, because again the energy would reach equilibrium. Now you again, this is the only two step you have to do. You have to just keep doing it again and again. So now you connect back to the battery. What happens? Now the cell that was low in charge, basically as in like low in voltage, it gets higher power capacitor. So what does that mean? The capacitor dumps the energy into it. So you literally can equalize multiple cells. Multiple cells and multiple different things. It's energy taking from here, auto equalizing, dumping. Taking energy, auto equalizing, dumping. That's how it works. So it's surprisingly effective. So you can have this sort of system, and it can literally have unhealthy battery packs, and it can make it useful again. And that's how exactly majority of your car, EVs and all that works. Without this sort of active balancing, no. So you can see that like these were there, resistor system will waste it. Active balancer will try its best to equalize it to the cell, and then you can see that like it's perfectly balanced. So you can use full of it and discharge full of it, charge full of it without wasting too much energy. So it's capacitor going series, like basically parallel to the cell, then going parallel to each other, then going to parallel to, it's like surprisingly efficient. There is an oscillator behind it. It's like surprisingly, it does work at very high frequency, kilohertz kind of frequency. Then you have something similar with inductive charger, which is used more, but I do not understand it same level as like capacitor. But apparently it uses the inductor at the same thing. Same thing is there, but only instead of capacitor is the inductor that is dumping the current. This also requires high frequency, like again, both of them actually balances the cell. So if you have unbalanced, this will be like, I got this. This will actually allow you to use more of your cell, more of your life, more safely, more long lasting. Meaning a battery pack that could have easily lasted you 4 years would only last 1 or 2 years if you use a passive system. This puppy is like, I'm gonna give you even more than that. So that's why it's a really, really wise way of doing it. Active balancing, either by capacitor, either by inductor, but you actively balance it. Basically take the energy from the full cells, dump it into partially charged cell, doing discharge, during charging, and it allows very long life. This is how you properly balance it. Those circuits are cut-off circuit. This is like, okay, I'm gonna solve the problem. That is like cut off, solve. So this is the active system. Then we come to the distributed topology. Now that sounds very complicated. It is complicated because it's used in huge packs. So whenever you are talking about like small voltages like 48 volts and all that jazz, you don't need to go too bonkers with it. But when you are talking about distributed topology, those are generally used in EV battery packs. Those puppy can go high voltage. What kind of high voltage? Well, EV starts at 400 volts. Some have double packs which go to 800 volts, and some are trying to go 1000 volts. So yeah, at that point in time, balancing becomes very difficult. Now again, from an engineering point of view, the best way of doing is like have every cell balanced. But yeah, that becomes unbearably complex to do. So what companies do is they build packs and each pack is treated as a cell from the motherboard. So you will build packs like this. You must have seen Tesla packs. There are packs like this, like you can see each of them is a pack. Each of them is a pack. The pack itself has multiple cells and a BMS dedicated to that pack itself. So it's like, hey, what's happening, what's going inside, it's gonna do whatever it needs to do. Now it has a communication bus that is communicating to the master or EV main BMS. That BMS will be like, okay, all the packs, hey, 48 volt, 48 volt, 48 volt, hey, that pack is like 36 volt. The pack inside would be balanced, but it itself would be like, compared to all other, it would be like, now pack itself does not know that's happening, but the balancer, the master balancer will be like, hey, that's off. That battery box is off. So it's gonna take energy from all of them and dump it to it. How they do it, in some designs they have transformers, some designs they have buck boost converter. There's a hell lot of hassle to do this, but that's how they do. So basically they make a lot of small pots and make it acting like think of it this way, like same way we have lead acid, but whenever you say lead acid battery, you assume it's a 12 volt. But imagine it this way, it's still 12 volt, but it has BMS inside. And BMS is communicating with the master battery system, where it's like, hey, I do not know the system of the whole thing, but I will gonna take care of the system. Basically, like, I'm taking care of this battery packs. I do not know what others are doing. I'm taking care of this. This is good. This is healthy. Or this is like faulty. It's going to send us a command signal. It's like, bro, faulty. What can you do at that point? Depending on the designer, some designers could have, if you have a lot of boxes, it could be possible to bypass one of them, one or two of them. But most of the time, it will just shut down your car. But let's see what happens. Again, only the car manufacturer knows what's actually gonna happen, unless you can, like, literally study the JTAG pins and like, okay, what's actually programmed in the microcontroller, you will not know this. So depending on the design, they could literally have like, hey, we have enough voltage, let's just bypass this pack. So person is like, not stuck. Most of the time it will be like undercharging or all that. So it can still be revived if, you connect it to a charger again. So battery packs requires a thing like this. So you have one small BMS per pack, and then you have a master BMS that's balancing each other. Now it does need a lot of communication and logic. To give you an idea of what kind of communication, the voltage wiring, it's not that difficult. But one automaker, when they were developing it, they gave up on the wiring part. Like, high voltage, good, done, go home. It's like JTAG wirings and all that, like I2C wiring and all that. It was becoming so complicated. They're like, okay, just eat all that puppy, put wireless communication, near field communication in that. I'm like, what? That was easier? Yeah, it was easier for them. It's like, dude, we had so many packs. It was just easier to have wireless communication. You will see that. You will see that in many, basically, battery banks. So they're like, dude, the wiring, the data communication wiring is so complex. It's like, just yeet that puppy, put wireless. So wireless communication happened to the vehicle BMS. Energy wiring is easy. It's just that BMS wiring becomes too hectic. And it does need logic. So back in the days, we had lithium iron phosphate, then we went to lithium ion and polymer, and then we are going back to lithium iron phosphate. So your BMS has to be wise. It needs to study what's the chemistry. It needs to know where it is in the flat curve. How should it react? It needs logic to it. It cannot be just like voltage this, I do this. It's like, it needs to be wise. It needs to balance it out. Otherwise, it could waste energy. So that's a serious issue. Now, why do companies go through this much hassle? Like, make small boxes and put them into bigger box? It allows for mass production. Could we design a system which has just one giant battery? Absolutely. It will just be very, very idiotically expensive. So mass production does not prefer that design. And it also makes them salvaging easy for us. So you can have Tesla went into accident. Most of the battery banks are intact. You just yeet that battery banks and use it as a solar battery. Many people do that. And from company's point of view, this also allows them, like, let's say Tesla built a battery system where each battery is 48 volt. Let's just go with that. And they're like, hey, for home, we do not want to exceed 48 volt. But what if we paralleled a lot of them for capacity? Okay, they can do that. They can do opposite also, that they could be like, hey, we are building a mega pack, and let's say that's for megawatt level of load. What if we scale connected a lot of them to 1000 volt? It can be done. So it does allow a lot of mass manufacturing flexibility, reliability, and all that jazz, while allowing some salvageable option. And a lot of people are focused on the salvaging part, because while the EV boom is happening, you have to understand, at some point it will go through a burst where, like, a lot of the primary cars that were used will reach a point where their batteries are like, hey, we need to replace it. What the hell are you gonna do? You could try to recycle it, but it will be too expensive and wasteful, simply because 80% of the horsepower is still there. It's just that it's not oomphish enough. So what can we do? If the packs are designed in this way, you can just yeet all the packs, put it as a second life for the battery, where you can use it on low drain loads, and it will still work. It will still have majority of its power. It can still work for 5 to 10 years extra. So having the sort of pack design does help. As long as you can manage the BMS, it should work just fine. So this is the distributed topology hassle that people have to go through. So if you have like, oh, I have 48 volt system and it's just one battery box, you're lucky. If you're like, hey, I have 92 volts, I have 3 packs, yeah, good luck. You have to deal with distributed topology. So this is the hassle part of it. So this is my presentation on basically the deeper dive of BMS, battery management system. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.